Hi, so today we're going to discuss Faraday's law of induction, motional electromotive force, Lenz's law, the induced electric field, inductance, RL circuits, energy stored in a magnetic field, mutual inductance, oscillations in an LC circuit, the RLC circuit, eddy currents, and magnetism in matter. So, we so far considered electric fields produced by stationary charges and magnetic fields produced by moving charges, right? But we will now consider electric fields produced by changing magnetic fields. And to show how an electric current can be induced by a magnetic field, let's consider a straight conductor in a uniform magnetic field directed into the page. So suppose the conductor moves to the right with a velocity v, and because there are free electrons in the conductor, a magnetic force will act on those electrons. And using the right-hand rule, and because the charge of the electron is negative, this force is directed downwards. So therefore, the electrons move along the conductor as a result of this magnetic force, which means a current is induced in the conductor when it moves in a magnetic field, okay? And another example is a loop of wire connected to an ammeter, as in this figure, which measures current. So if a magnet moves towards the loop, a current is induced in the loop, which is revealed by the ammeter, okay? And if the magnet is held stationary, the ammeter reading will be 0. And if the magnet is moved away from the loop, a current is induced in the loop, but in the opposite direction to the one when the magnet was moving towards the loop. Okay. Also, if the magnet is held stationary and the loop is moved either towards or away from the magnet, a current is also induced in the loop. And so this shows that a current is induced in the loop if there is a relative motion between the magnet and the loop, okay? And this type of current that is not produced by a battery is known as an induced current. And the electromotive force that produced it is known as an induced electromotive force, okay? So an experiment conducted by Faraday is shown in this figure here, where it shows a primary coil connected to a battery and a secondary coil connected to an ammeter. So the coil is wrapped around iron to intensify the magnetic field that the coil produces. So at the instant the switch here in the primary circuit is opened or closed, the ammeter here shows a current for a short time, then it returns to 0. And the direction of the current when the switch is closed is opposite to its direction when the switch is opened, okay? And so after some time of the switch being closed, the reading in the ammeter is 0. Even though there is a steady current in the primary circuit, okay? The reading of the ammeter still remains 0. So there's a current only for a very short time during when the switch is opened or closed. And from these observations, Faraday concluded that an electric current is produced by a time-varying magnetic field. And so a constant magnetic field does not produce a current. And this is why the current is induced at the instant the switch is opened or closed, because during that time the magnetic field in the secondary coil changes with time. And then it induces a current in this secondary coil as though it is connected to a source of electromotive force during that short time, okay? So the primary circuit produces a magnetic field which changes with time from 0 to a maximum value or from maximum value to 0 in this short time as the switch is closed or so to understand this, we will define a quantity known as the magnetic flux. which is proportional to the number of magnetic field lines passing through an area. Okay, the same way the electric field flux is proportional to the number of electric field lines passing through an area. So consider this arbitrary shape here shown. If the magnetic field at the location of the element area dA is B, then the magnetic flux through that element is B dot dA, okay, where dA is a vector perpendicular to the surface element of area dA. And so the total magnetic flux phi B is equal to integration of B dot dA. So the SI unit of the magnetic flux is Tesla times meter square, which is Weber, known as the Weber, okay? And so Faraday's law of induction states that an electromotive force E is induced in a circuit if the magnetic flux phi B through the surface bounded by the circuit changes with time, okay? So the induced electromotive force is equal to the time rate of change of the magnetic flux through the circuit. So this is Faraday's law of induction. Okay, so phi B is the magnetic flux through the surface bounded by the circuit, and the minus sign follows from Lenz's law, which we will discuss shortly. So if the circuit consists of n identical loops, and if the magnetic field lines pass through all of the loops, okay, then the induced electromotive force is given by this equation, which shows that the induced electromotive force is n times greater than that for one loop. And this is because all the loops are in series, and the electromotive forces for the individual loops will add up to give the total electromotive force, okay? So for this loop here, shown, the flux is equal to integration of B dot dA, and since B and theta is constant, we can take them out of the equation. And the integration of dA is A, okay? And so the induced electromotive force is minus d over dt BA cosine theta. So this shows that an electromotive force E can be induced in a circuit by changing the magnetic flux, either through changing the magnitude of B with time, or changing the area A of the circuit with time, or changing the angle theta between B and the normal to the loop with time, or by combination of these conditions. So let's consider the following example where a loop of radius of 2 centimeters is placed in a uniform magnetic field of 0.2 Tesla, and then it is rotated by an angle of 45 degrees with a constant angular speed during a time interval of 0.5 seconds, okay? And we want to find the induced electromotive force in the loop due to the change in flux, okay? When B is parallel to the normal to the loop, the magnetic flux is given by this equation. So phi B is equal to BA, and this is equal, it will give us 2.5 times 10 to the minus 4 Weber. And when the angle between B and the normal to the area is 45 degrees, the magnetic flux through the loop is given by this equation, and it gives 1.3 times 10 to the minus 4 Weber. So using Faraday's law, the average induced electromotive force is minus delta phi B over delta T, and it's we substitute for phi B, and we divide by 0.5 seconds, and this gives us an electromotive force of 2.4 times 10 to the minus 4 volts. So let's consider two more examples. So in this example here, the magnitude of B changes linearly with time from B is equal to 0 to B is equal to 0.2 Tesla. And its orientation remains parallel to the normal to the loop. And the radius, we take it similar to this example, 2 centimeters, okay? So the absolute value of the induced electromotive force is equal to delta phi B over delta T, which is equal to the area A, which is pi r squared, times B final minus B initial over the time, 0.5 Tesla, sorry, 0.5 seconds. And the angle is 0, so cosine 0 is 1. And therefore, we get this induced electromotive force, 5 times 10 to the minus 4 volts. And we consider also another example in which the magnitude of the magnetic field changes exponentially with time, according to this expression, where alpha here is a constant, okay? So at t is equal to 0, B is equal to maximum, and for t greater than 0, the magnitude of the field will decay exponentially with time, like that, okay? Exponential curve. And the induced electromotive force in the loop is a function of, as a function of time, is given by this equation. So because we have just one turn, so n is equal to 1, and the differentiation of this will give us alpha a b max e to the power minus alpha t. So this shows that the induced electromotive force also decays exponentially with time, and the maximum induced electromotive force is given by alpha a b max. So we will now consider the motional electromotive force, which is the electromotive force induced in a conductor when it moves in a magnetic field. So consider the conductor shown here moving with a constant velocity that is perpendicular to a uniform magnetic field directed inwards into the page. So the force experienced by the electrons in the conductor is Fb equal to QVB, and this force will cause the electrons to accelerate downwards, leaving a net positive charge in the upper end of the conductor, okay? So therefore, due to this charge separation, an electric field E directed from the positive to the negative is produced in the conductor. So this buildup of charge will continue as the conductor moves until the magnetic force QVB on the electron directed downwards is balanced by the electric force directed upwards. So the net force of the electron is then equal to 0. So when the net force on the electrons is 0, the charge will stop flowing, and we have QE is equal to QVB. And this electric field that is produced inside the conductor is uniform, and therefore we can relate it to the potential difference delta V across the ends. So delta V is equal to EL, and L is the length of the conductor, which is equal to BLV. And so the upper end here, the positive, is at a higher potential than the lower end, okay? And so as long as the conductor is moving in the magnetic field, a potential difference is maintained in the conductor. So if the moving conductor is part of a closed circuit, as in this figure, and the bar slides along two frictionless conductors, and let's assume that the bar has 0 resistance, and that the resistance of the circuit is R, and that a uniform magnetic field B is applied perpendicular to the plane of the circuit directed into the page. Then as the bar moves with a velocity v, by an applied force F applied, the free charges in the bar will experience a magnetic force along the bar, and a continuous current is established in the circuit, right? Okay, and the magnetic flux through the circuit is phi B is equal to BLX, where LX is the area of the circuit. So using Faraday's law, E is equal to minus d phi B over dt is equal to minus d over dt BLX, which is equal to minus BLV. So the magnitude of the induced current in the circuit I is equal to E over R, which is equal to BLV over R, where R is the resistance of the circuit, And an equivalent circuit is shown here where the moving bar behaves as a battery and a source of electromotive force as long as the bar is moving in the magnetic field, okay? And the magnetic force Fb experienced by the bar magnet as a whole by this bar magnet is equal to ILB, where I is the current induced in the circuit due to the bar's motion. And this force is directed to the left, opposing the applied force. And because the bar is moving with a constant velocity, this force is equal in magnitude and opposite in direction to the applied force. Okay. So the total work done on the system by the applied force while the bar is moving with a constant speed is equal to the increase in the internal energy of the resistor, okay? Assuming the energy stays in the resistor and does not leave through heat or electromagnetic radiation. So therefore the power delivered by the applied force P is equal to F applied V is equal to ILB V, and this is equal to BLV over R square times R, which is equal to I square R, and this is equal to the rate at which energy is delivered to the resistor, okay? So let's suppose as an example that the bar is given an initial velocity of V initial and then is released without any applied force. So it's given initial velocity and is left to slide, okay? Because the magnetic force acting on the bar is to the left opposite to the motion of the bar, then it will decelerate. The bar will decelerate and the force Fx is equal to ma. So because these bars are frictionless, the only force is the magnetic force equal to minus ILB is equal to mdv over dt. Okay, and if we rearrange this, we get this equation. If we integrate from V initial to V, we get ln V over V initial is equal to minus B square L square over MRT, and this is equal to V is equal to V initial e to the minus T over tau, and tau is equal to MR over B square L square. And this shows that the velocity of the bar decreases exponentially with time, okay? So we will now discuss the alternating current generator, which is a device that transforms mechanical energy to electric energy, okay? So an external agent rotates the loop in an external magnetic field, and the energy required to rotate the loop can come from different sources, such as from falling waters in a hydroelectric plant or from burning coal that converts water into steam, which is then used to rotate the loop, okay? So as the loop rotates, the magnetic flux in the loop changes with time, and this will induce an electromotive force which produces a current in a circuit connected to the loop, okay? So suppose there are n turns in the coil here. So there are n loops and all of them have the same area A. And if the angular speed of the loop is constant and is equal to omega, and it rotates about an axis perpendicular to the magnetic field, and if theta is the angle between the magnetic field and the line perpendicular to the plane of the loop, okay, then the magnetic flux at any time through one loop is BA is equal to BA cosine theta, which is equal to BA cosine omega t. And therefore, the induced electromotive force is E is equal to minus N d phi B over dt, and this gives NBA omega sine omega t, okay? So a plot of this electromotive force is shown here, where it varies sinusoidally with time, okay? The maximum electromotive force is NBA omega, which occurs when omega t is equal to either 90 degrees or 270 degrees, which is when the magnetic field is in the plane of the coil and d phi b over dt is maximum. And this electromotive force is zero when omega t is either equal to 0 or 180 degrees, which is when the magnetic field is perpendicular to the plane of the loop, okay? So this sinusoidal electromotive force is the source of an alternating current and is known as an AC voltage, okay, as opposed to the DC voltage from a battery. So in this section, we will discuss the source of the negative sign in Faraday's law, which is Lenz's law, and this law determines the direction of the induced electromotive force and the induced current when the magnetic flux changes, okay? And Lenz's law states that the direction of the induced current in a loop is such that as to create a magnetic field that opposes the change in the magnetic flux through the area enclosed by the loop, okay? So, in other words, Lenz's law states that the induced current tends to keep the original magnetic flux from changing. So going back to the sliding bar example, so as the bar moves to the right, the magnetic flux through the circuit will increase with time because the area of the loop is increasing, okay? So Lenz's law states that the direction of the induced current must be such that as to produce a magnetic field that opposes the change in the magnetic flux of the external magnetic field. And since the flux of the external magnetic field directed into the page is increasing, the induced current must produce a magnetic field out of the page, okay, to oppose this change, okay, and that is why the induced current is counterclockwise to give a magnetic field out of the page. So if the bar moves to the left, the magnetic flux through the loop will decrease with time, and the induced current must be clockwise to produce a magnetic field into the page to oppose this decrease in the external magnetic field flux, okay? So in either case, the induced current tends to maintain the original flux through the circuit. And also from an energy view consideration, if, for example, in this case where the bar is moving to the right, we assume that the current is clockwise, the induced current is clockwise. In that case, the direction of the magnetic force, ILB, on the bar will be to the right, okay? And this will accelerate the bar to the right, increasing its speed, which in turn will cause the area of the loop to increase more rapidly. And this will in turn increase the induced current, which will increase the force, which will increase the current, and so on. And this would violate the law of conservation of energy because in this case the system would be acquiring energy with no additional input energy. And this is why the induced current in this case must be counterclockwise. So we will now discuss the induced electric fields. So we have seen how a changing magnetic flux induces an electromotive force that induces a current in the loop. And so we can interpret the changing magnetic field as creating an induced electric field in the conductor, okay? Because the flow of charges or current in the loop must be due to an electric field, okay? And so we conclude that an electric field is always created by a changing magnetic flux, even in free space where no charges are present. So let's consider a conducting loop of radius r, as shown here, placed in a uniform magnetic field that is perpendicular to the plane of the loop. If the magnetic field changes with time, then the induced electromotive force is equal to minus d phi b over dt, okay? And it will induce a current in the loop. And this current implies the presence of an induced electric field E tangent to the loop to provide the electric force that drives the motion of the charges around the loop, okay? So the work done by the electric field in moving a test charge Q once around the loop is equal to QE. And this work can also be expressed in terms of the electric field through this equation. So W is equal to integration F dot dr is equal to QE 2 pi r, where 2 pi r is the circumference of the loop. So if we equate these two equations, we get this expression for E, and if we substitute for Faraday's law for E, we get this expression. And the minus sign indicates that the induced electric field E produces a current that opposes the change in the magnetic field. And as we said, this electric field is induced even in empty space in the absence of a conductor or charges, okay? So the magnitude of the electromotive force for any closed path can be expressed in this way. So E is equal to closed integration of E dot ds, and we may write this equation here, okay? So note that this induced electric field E is a non-conservative field because the work done in moving a charge around a closed path by this field is not zero, okay? And so this electric field produced by a changing magnetic field is different from the electrostatic field produced by stationary charges, okay? So for this equation, let's consider an example. Suppose that we have a magnetic field that is uniform over space and is changing in magnitude, where it is increasing at a constant rate. So this rate is constant. Then you can see from this equation that the induced electric field has a constant magnitude. So let's consider the example of the induced electric field due to a changing magnetic field in a solenoid. So we have a long solenoid of radius r and n turns per unit length that carries a time-varying current that varies sinusoidally with time, as this equation, I is equal to I max cosine omega t, and I max is the maximum current and omega is the angular frequency of the alternating current source. So we want to find the magnitude of the induced electric field outside of the solenoid at a distance of r greater than r, okay, from the central axis. So because the current is varying with time, it will produce a changing magnetic field, and this will lead to an induced electric field, okay? So first we want to calculate the change in the magnetic flux for this path shown. So you can see here that the magnetic field inside the solenoid is perpendicular to this is perpendicular to the circle bound by this path, okay? And all of the lines pass through this area. So the change in the magnetic flux is equal to minus d over dt b pi r square, which is equal to minus pi r square dB over. So from the previous example, in the previous video, the magnetic field inside the solenoid is given by mu naught Ni equal to mu naught Ni max cosine omega t. And so the change in the magnetic flux is given by this equation. So we differentiate cosine omega t is equal to omega sine omega t. And the closed integration of E dot ds around this path is E times 2 pi r. And so we equate this equation with this, and we get, so from here we get E is equal to mu naught n I max omega r squared sine omega t over 2r for the region r greater than r, okay? So this shows that the amplitude of the electric field outside the solenoid falls as 1 over r, and the field varies sinusoidally with time. And we will see in later videos that this time-varying electric field creates an additional contribution to the magnetic field, but is small if the frequency is small. But at high frequencies, the varying electric and magnetic fields constitute an electromagnetic wave radiated by the solenoid, okay? So now for the region R less than R, the magnetic flux, we will take a path inside the solenoid, and the change in the magnetic flux is given by this equation. And if we substitute for I and we equate with the line integral around this path inside the solenoid, we get this equation for E, okay? And so the amplitude of the electric field induced inside the solenoid increases linearly with R, as you can see here, right? And it also varies sinusoidally with time. So we will now consider inductance. So consider this circuit shown here. When the switch is closed, the current doesn't immediately jump from 0 to E over R, and this can be explained by Faraday's law. So because as the current increases with time, the magnetic flux through the loop also increases with time. And this increasing magnetic flux produces an electromotive force, also known as a back electromotive force, in the circuit that opposes the change in the net magnetic field through the loop, okay? And by Lenz's law, the induced electric field in the wires is opposite to the direction of the current, and so this opposing electromotive force results in a gradual increase in the current. And this effect is known as self-induction, okay, because the changing magnetic flux through the circuit is from the circuit itself, and the electromotive force induced is known as the self-induced electromotive force. So for a coil of n turns, the self-induced electromotive force is equal to minus n d phi b over dt and is equal to minus L di over dt. And L is a proportionality constant known as the inductance of the coil, and it depends on the geometric features of the coil and other physical characteristics. Therefore, the inductance of the coil of n turns is equal to n phi b over I, and that is assuming that the same magnetic flux passes through each turn, okay? And also we may write the inductance as minus EL over di over dt. And if we compare this equation to the resistance R equal to delta V over I, you can see that resistance measures the opposition of a current, whereas inductance measures the opposition to the change in the current. So the SI units of inductance is the Henry, so 1 Henry is equal to 1 volt times second over ampere. And we shall now see that inductance of a coil depends on its geometry. So let's consider the example of a solenoid. If we have a solenoid with n turns and of length L, where L is much longer than the radius of the solenoid, and let the core of the solenoid be air, then the magnetic flux through each loop of the solenoid of area A is equal to BA. And we have seen in the previous video that the magnetic field inside the solenoid is mu naught Ni. So the flux is equal to mu naught N over L Ia, because here N is the number of turns per unit length, okay? And from this we find the inductance of the solenoid is equal to mu naught N square over L A. And if we substitute N is equal to small n times L square, then we get mu naught N square V, where V is the volume, the interior volume of the solenoid, okay? And the self-induced electromotive force in the solenoid, if the current is increasing or decreasing, can be found from this equation. So we will now discuss RL circuits. So a circuit element with a large inductance is known as an inductor, and its symbol is a coil like this one. And the inductance of the remaining of the circuit is usually neglected compared to that of the inductor, okay? When the switch S1 is closed, the inductance in the inductor causes a back electromotive force that opposes the change in the current in the circuit, okay? And so the rise of the current when the switch is closed is not instantaneous due to the presence of the inductor, okay? And also, if the switch is opened, the current will decrease and the inductor will cause a slow decrease of the current rather than a sudden drop. And so the inductor slows the reaction of the circuit with the changes in voltage. So consider this circuit here, known as an RL circuit, and suppose S1 is closed and the current in the circuit starts to increase. Then, as we said, a back electromotive force that opposes this increase in current will be induced in the inductor, okay? So if we apply Kirchhoff's law to the circuit in the clockwise direction, we have this equation E minus IR minus L di over dt is equal to 0. And note here that Kirchhoff's law was developed for a circuit with a steady current, but we can also apply it to a circuit where the current is changing if we apply it at one instant of time, okay? We can use this change of variables. So x is equal to e over r minus I, and dx is equal to minus di. And we substitute, and then we integrate, and we get ln x over x naught is equal to minus r over L t. And this gives x is equal to x naught e to the minus rt over L. We substitute here for x. And so I is equal to e over r 1 minus e to the power minus t over tau, and tau is the time constant equal to L over r, okay? So this shows that due to the inductor, the current does not increase instantly to its equilibrium value E over R when S1 is closed, but it increases as an exponential function, okay? So the time rate of change of the current, if we differentiate I, is given by this equation. And this shows that the time rate of change of the current is maximum once the instant we close the switch S1, so at t is equal to 0. And this maximum time rate is E over L. And this rate slows down with time, okay? So first the current increases rapidly, then it gradually approaches E over R as t goes to infinity. So now suppose after the circuit has reached its equilibrium current value of E over R, that the switch S2 is close to this position, okay? Then the battery will be out of the circuit and E will be equal to 0. And we have now this equation. So IR plus L di over dt is equal to 0, which has this solution. Okay, and so for this circuit, when we close S2 and the battery is no more part of it, the current decreases exponentially with time to 0, okay? And this is due to the presence of the inductor. So if the inductor is not present, and we assume the inductance of the remaining of the circuit to be negligible, then the current will decrease immediately to 0 when the battery is removed. And it also, if S2 is put in this position for our initial circuit when the battery was included, it will increase, the current will increase instantaneously to its equilibrium value E over R if there was no inductor, okay? So we will now discuss energy stored in a magnetic field. So when S1 is closed, as we have seen, the inductor prevents the current to rise instantaneously to its steady state value of E over R, okay? And during that time, part of the energy supplied by the battery goes as internal energy of the resistor, and the other part is stored in the conductor. So multiplying Kirchhoff's equation by I, we get this equation. So the rate at which energy is supplied by the battery, IE, is equal to the rate at which energy is delivered to the resistor, I square R, plus the rate at which energy is delivered to the inductor, Li di over. And so this is a statement of the conservation of energy if the circuit is isolated. If it's not isolated, some energy will leave the resistor through heat or electromagnetic radiation. So let the energy stored in the inductor at any time be U. Then the rate du over dt at which energy is delivered to the inductor is equal to Li di over dt. And the total energy stored in the inductor at any instant is the integration from 0 to u to du and is equal to half Li square, where L is a constant. So this energy represents the energy stored in the magnetic field of the inductor when the current is I. And this form is similar to the energy stored in a capacitor, which is equal to half C delta V square, where in both cases part of the energy supplied by the battery is stored in the field, which is the electric field in the case of a capacitor and the magnetic field in the case of the inductor, okay? So to find the energy per unit volume or energy density stored in a magnetic field, let's consider a solenoid whose inductance is given by this equation, and the magnetic field in the solenoid is mu naught Ni, okay? So we substitute for L and I, which is B over mu naught N, in this equation, and we get B square over 2 mu naught AL. And AL is the volume of the solenoid. So if we divide by the volume to get the energy density, we get UB is equal to B square over 2 mu naught. Although this expression was derived for a solenoid, it is valid for any region of space containing a magnetic field, okay? And note how this form is similar for the energy density stored in an electric field, which is half epsilon naught E square, where in both cases the energy density is proportional to the square of the field, okay? So now let's suppose after the current reached a steady state value of E over R, we then put the switch S2 to this position, and if we assume the circuit to be isolated so that no energy leaves the system, then if S2 is closed here, energy is now delivered to the resistor only from the inductor, okay? Because the battery is no longer part of the circuit. And eventually, all of the energy that is initially stored in the magnetic field of the inductor will appear as internal energy in the resistor, assuming the circuit is isolated and no energy leave the resistor through heat or electromagnetic radiation. And you can show this by considering the rate at which energy is leaving the inductor, which is du over dt, and equate it to the rate at which energy is delivered to the resistor, which is I square R. And for this circuit, when the battery is not part of it, the current will decay exponentially with time, as we have seen in the previous slide. And so if we substitute for I, and then if we integrate for u from t is equal to 0 to infinity, we get this expression for u, which is half Li initial square. And this is the initial energy stored in the magnetic field of the conductor. So all of this energy will eventually be delivered to the resistor. So we will now consider mutual inductance. So sometimes the magnetic flux through a circuit varies with time due to a varying current in a nearby circuit, okay? So this will induce an electromotive force in the second circuit due to the first in a process known as a mutual inductance, okay? So consider two coils next to each other. If I1 is the current in coil 1, which has N1 turns, it will have a resulting magnetic field due to this current, right? and some of the lines of its magnetic field will pass through coil 2, which has N2 turns. Okay? So the flux through coil 2 produced by coil 1 is phi 2 1, and we define the mutual inductance M21 of coil 2 with respect to coil 1 equal to N2 phi 21 over I1. Okay? So this mutual inductance depends on the geometry of both circuits and on their orientation with respect to each other. And as the separation between the coils increases, the mutual inductance decreases due to the decreased flux, okay? So if I1 varies with time, then from Faraday's law, we have the induced electromotive force in coil 2 is equal to minus N2 d phi 21 over dt, and this is equal to minus M21 di1 over dt. And in a similar way, if I2 in coil 2 varies with time, then the induced electromotive force in coil 1 is equal to minus M12 di2 over dt. So the electromotive force induced in one coil is proportional to the rate of current change in the other coil. So if di1 over dt is equal to di2 over dt, then E1 is equal to E2, okay? And also it can be shown that M21 is equal to M12 is equal to M. And so we may write E2 and E1 in this form. So as an example, let's consider a long solenoid of length L and N1 turns carrying a current I1 and of cross-sectional area of A. And there is a second coil of N2 turns with the same cross-sectional area. These turns are concentric with the first, okay? So we want to find the mutual inductance of the system. So the magnetic field due to the first solenoid of N1 turns and current I1 is equal to mu naught N1 I1 over L, okay? And since the flux through coil 2 due to coil 1 is phi 21 and is equal to BA, so we may write the mutual inductance as N2 phi 21 over I1 is equal to N2 BA over I1, and this is equal to mu naught N1 N2 A over L. So we will now discuss oscillations in an LC circuit. So if a charged capacitor is connected to an inductor and the switch is closed, then both the current in the circuit and the charge on the capacitor will oscillate with time. If the resistance of the circuit is assumed to be zero, then no energy is lost as heat and the oscillation will persist. So suppose the initial charge of the capacitor is Q max and the switch is closed at t is equal to 0. So initially the total energy U in the circuit is stored in the electric field of the capacitor and is equal to Q max square over 2C. And the current in the circuit is 0 and no energy is stored in the inductor. But as the capacitor charge starts to discharge, the energy stored in the capacitor will decrease and the current in the circuit will increase, and some of the energy will be stored in the magnetic field of the inductor. When the capacitor is fully discharged, it stores no energy and the current in the circuit reaches a maximum value, and all of the energy is then stored in the inductor, okay, as half L I max square. And then the process repeats itself, but in the reverse direction, and the energy continues to oscillate between the capacitor and the inductor indefinitely, okay? So let's consider an arbitrary time, t, after the switch is closed. At that time, the capacitor's charge is Q, and the current in the circuit is I, and both the capacitor and the inductor store energy. And the sum of the two energies is equal to the total initial energy U, which was Q max square over 2C, stored in the fully charged capacitor at t is equal to 0. So we have U is equal to UC plus UL equal to Q square over 2C plus half L I square. Uh, so since we assumed the resistance of the circuit to be 0, then no energy is dissipated as heat, and therefore the total energy must remain constant at all times. So the differential with time of the total energy is equal to 0. And this gives this equation, okay? And since I is equal to dq over dt and di over dt is equal to d square, the second differential of the charge, then we get this equation, okay? And from this, we get this equation, which has a similar form of the simple harmonic oscillator of a mass spring system, as we have seen in the videos of mechanics, which is d square x over dt square is equal to minus k over m x, which is equal to minus omega square x. And it has a solution of the form Q is equal to Q max cosine omega t plus phi, where omega is equal to 1 over square root of LC. So Q max is the maximum charge of the capacitor. So because Q varies harmonically, the current also varies harmonically. Okay. So if we differentiate the charge, we get this equation for the current, and the value of the phase angle phi can be determined from the initial conditions. Okay, so for this case, at t is equal to 0, I is equal to 0, and q is equal to q max. And so if we substitute in the equation for I, we get this this equation, we get 0 is equal to minus omega q max sine phi, and we get the phase angle is equal to 0. And this phase angle is consistent with the fact that at t is equal to 0, q is equal to q max, okay? So q is equal to q max cosine omega t, and I is equal to minus omega q max sine omega t, which is equal to minus I max sine omega t, okay? Where, so I max is the maximum current in the circuit, and is equal to omega q max. So as you can see from the graphs here, the charge on the capacitor varies between q max and minus q max, and the current also oscillates between I max and minus I max. And as you can see, the current is 90 degrees out of phase with the charge. So this is a cosine function and this is a sine function, okay? And this means that when the charge is maximum, the current is 0, and when the charge is 0, the current is maximum. And so we have U is equal to UC plus UL, and we substitute for Q, Q max square over 2C cosine square. So we substitute for Q this equation, and we substitute for I this one, and also so this shows that the energy of the system continuously oscillates between the energy stored in the electric field of the capacitor, okay, and the energy stored in the magnetic field of the inductor. So the energy is going back and forth between the two. And so when the energy stored in the capacitor is maximum, the energy stored in the inductor is 0, and vice versa. And so since the total energy is constant, so Q max square over 2C is equal to Li max square over 2, then we can substitute here Q square max over 2C. and we get this expression, and we know that sine square plus cosine square is equal to 1, and so the total energy is equal to this, okay? And note that here we consider the ideal situation in which the resistance of the circuit is assumed to be 0, but in actual circuits there is always some resistance, okay? And so the total energy will be lost as heat, and also even if energy losses due to resistance are neglected, energy will also be lost in the form of electromagnetic waves radiated by the circuit. So we will now consider the RLC circuit, which is the more realistic circuit, and it consists of an inductor, a capacitor, and a resistor, okay? And we assume that the capacitor has an initial charge of Q max before the switch is closed. And once this switch is closed, the current is established in the circuit. The total energy stored in the circuit at any time is as before given by Q square over 2C plus half Li square, okay, as in the previous slide. But in this case, due to the resistance in the circuit, this total energy is no longer constant and is dissipated with time as heat. So since the total energy is no longer constant, its differential is not constant but is equal to minus is not zero, sorry, but is equal to minus I square R, and I square R is the rate of energy dissipation through the resistor. So the negative sign indicates that U is decreasing with time, and so we have, if we differentiate U and we substitute for I as dq over dt and the differential of I as d square q over dt square, and then we rearrange, we get this equation. And this is analogous to a damped harmonic oscillator, which has this form, okay? So in the case of light damping, when R is small, the resistance is small, the solution is given by this form, where the frequency omega d is equal to this value, okay? So this shows that the charge oscillates in damped harmonic oscillations. So the oscillation dies out with time. And because the current is the differential of the charge, the current also undergoes damped harmonic oscillations, okay? So you see here that the maximum value of Q decreases after each oscillation the same way the amplitude of a damped harmonic oscillator decreases with time. So we will now discuss eddy currents. So as we have seen, a changing magnetic flux in a circuit induces an electromotive force and a current. In this same way, circulating currents known as eddy currents are also induced in bulk pieces of metals if they move in a magnetic field. So the changing magnetic flux will induce eddy currents, okay? So let's consider a copper plate attached to a bar and swinging as a pendulum in a magnetic field. So as the plate enters the field, the changing magnetic flux induces an electromotive force in the plate, which causes the free electrons in the metal to move and produce swirling currents, okay? So using Lenz's law, the direction of the eddy currents must oppose the change of the magnetic flux, okay? And also these eddy currents create their own magnetic field, producing effective magnetic poles on the plate that are repelled by the poles of the external magnet, okay? And this repulsion force opposes the motion of the pendulum. As you can see here, this force is opposite to the motion. So you can see here that the eddy current produced as the plate enters the field, the magnetic flux into the page will increase, right? And by Lenz's law, the induced current loop must give a flux out of the page to oppose this change, and that is why the eddy current is counterclockwise. So the opposite is true when the plate is leaving the field. Then the magnetic flux into the page will be decreasing, and the eddy current will be clockwise. Okay, to oppose this decrease. And the retarding force due to eddy currents, as you can see, is opposite to the motion um, when the plate either enters or leaves the field, and therefore the swinging plate will eventually come to rest. So we will now discuss the magnetization and the magnetic field strength. So the magnetic state of a substance is described using a quantity known as the magnetization vector m, okay? And the magnitude of this vector is equal to the magnetic moment per unit volume, okay? So the value of the magnetic moment per unit volume of the substance. The total magnetic field in a substance depends on both the magnetization of the substance itself and the external applied magnetic field. And so if a magnetic field B naught, an external magnetic field B naught exists in a region due to a current carrying conductor, and if in that region a magnet or a magnetic substance is placed in that region, then the total magnetic field B in the region is given by B naught plus Bm, where Bm is the field produced by the magnetic substance, okay? So in terms of the magnetization vector, the magnetic field produced by the substance Bm is equal to mu naught m. Okay, and also a useful quantity is known as the magnetic field strength H, and it is equal to B over mu naught minus M, okay? And so B is equal to mu naught H plus M. The SI units of both of either H or M is ampere per meter. So we will now consider the classification of magnetic substances. So for many substances, specifically paramagnetic and diamagnetic materials, the magnetization vector M is proportional to the applied magnetic field strength H. According to this equation, where chi is a dimensionless factor known as the magnetic susceptibility. So if the substance is paramagnetic, then chi is positive and therefore M has the same direction as H. And if the substance is diamagnetic, then chi is negative and M is in the opposite direction to H. But this linear relationship between M and H does not apply in the case of ferromagnetic materials. So if we substitute for M, we get this expression, and we may write it as B is equal to mu M H, and the mu M is the magnetic permeability of the substance, okay? And is equal to mu naught 1 plus chi. And so the materials can be classified as paramagnetic if mu M is greater than mu naught, diamagnetic if it's less, and ferromagnetic if it's much larger than mu naught, okay? Also note that, as we said, for ferromagnetic materials, M is not a linear relationship or a linear function of H, okay? And and also mu M for a ferromagnetic materials is not a characteristic of the substance, but it depends on the previous state of the sample. So as an example, we will consider a toroid with an iron core. So suppose we have a toroid with 60 turns per meter carrying a current of 3 amperes. And if its core is made of iron, which has, in these specific conditions, a magnetic permeability of 5000 mu naught. Okay, then we want to find the magnetic field strength H and the total magnetic field B inside the iron. So the magnetic field B naught due to the current in the toroid without considering the iron, okay, just this is considered the external magnetic field, can be calculated from this equation, and therefore the magnetic field strength is given by this, and this gives us 180 amperes times turns per meter. And if you want to find the magnetic field B inside the iron, so this will include the effect of the magnetic material. And so the total magnetic field is given by this equation, which is 1.1 Tesla. And this is 5,000 times greater than the value of B naught, okay? And the magnitude of the magnetization vector can be found from this equation, and it is 9 times 10 to the power 6 amperes per meter, and it has the same direction as H. So we will now discuss ferromagnetism. So some crystalline materials that have permanent magnetic dipole moments exhibit strong magnetic fields and are known as ferromagnetic materials. Examples are iron, cobalt, and nickel. The magnetic moments in such materials tend to align parallel to each other even if a weak external magnetic field is applied. And once those magnetic moments align, the substance remains magnetized even if the external magnetic field is removed. And this permanent alignment between the magnetic moments is due to the strong coupling between neighboring moments and can be explained by quantum mechanics. So the ferromagnetic substance consists of microscopic regions known as domains in which the magnetic moments are aligned in each domain in a certain direction. Okay? So each domain has a volume of approximately 10 to the minus 12 to 10 to the minus 8 meter cubed and contains about 10 to the 17 to 10 to the 21 atoms. And these boundaries here between domains with different orientations are known as domain walls. So if the sample is unmagnetized, like this sample, the domains are randomly oriented, as you can see, so that the net magnetic moment is zero because they cancel each other out, okay? But if the sample is placed in an external magnetic field, the magnetic moments of some domains tend to align with the field, and this results in a magnetized sample. So in that case, the domains here that are initially oriented with the external field grow in size at the expense of the less oriented domains. Okay. And even after the external field is removed, the sample may retain a net magnetization in the direction of the original field. Okay. And also in ordinary temperatures, the thermal agitation is not sufficient to disturb the dominant orientation of the magnetic moments. So a configuration known as the Rowland ring here is shown and is used to measure the magnetic properties of a ferromagnetic material, and it consists of a toroid with a wire of N turns around it. So another secondary coil is connected to a galvanometer and is used to measure magnetic flux. So the magnetic field B within the core of the toroid is measured by increasing the current in the primary in the primary coil here from 0 to I. And as the current changes, the magnetic flux through the secondary coil will change by BA. Okay, where A is the cross-sectional area of the toroid. And this changing magnetic flux induces a current in the secondary coil that is proportional to the rate of change of the magnetic flux. So from this measurement of the current, the value of B, which is the total magnetic field in the toroid, can be obtained. So now suppose the core of the toroid consists of an unmagnetized iron. So if the current in the primary coil is increased from 0 to I, then the field intensity H increases linearly with I. The field intensity is the magnetic field produced by the current in the coil. Okay, so it increases linearly with I according to the equation H is equal to Ni, as we saw in the previous slides, okay? So then the total field B inside this core will also increase with H. It will increase with this external magnetic field. And remember that the total magnetic field B includes the contribution of the external magnetic field, which is due to the current in the coil, and also includes the contribution of the magnetic field produced by the material itself due to the alignment of its magnetic moments with the external field, okay? And so this contribution of the material itself is also a function of the external field. So this figure here shows a plot of the total magnetic field B in this core here versus H, which is the external magnetic field produced by the coil. And this is known as the magnetization curve. So at point O, the domains are randomly oriented, which means the magnetic field produced by the material Bm is equal to 0. As the external field increases, the domains become more aligned, and this will increase until all are nearly aligned at A, which corresponds to the iron here at A reaching saturation, which is the condition when all domains are aligned in the same direction, okay? So if now the current in the primary coil is reduced to 0, then the external field H will also reduce to 0, right? And in this case, B will decrease according to the curve AB here, okay? So this shows that even when H reaches 0, the total field B is not 0. So this is because the iron core is now magnetized due to a large number of domains being aligned. Okay, so B here, the total magnetic field is equal to Bm, and therefore the iron has a remnant magnetization. Okay, so now suppose the external field H is reversed in direction by reversing the current in the primary coil, and this current is increased in strength. Then the domains will reorient until the iron is unmagnetized at the point C, where the total magnetic field here is 0. And the increase in the reverse current will cause the iron to be magnetized in the reverse direction, okay, where it approaches saturation at the point D. And if the current is again decreased to 0 and then increased again in its original direction, then the magnetization curve follows the path DEF, okay? And if the current is increased sufficiently, then the curve will reach the point A again, which is a point of saturation. So this curve here is known as the magnetic hysteresis loop, and it shows that the magnetization of a ferromagnetic material depends on the history as well as the strength of the applied field, okay? And the shape and size of this loop depends on the properties of the ferromagnetic material and on the strength of the applied field. The hysteresis loop for hard ferromagnetic materials is wide, as in this case, which means it has a large remnant magnetization, right? So the value here of the remnant magnetization is large. So it also means that such a material cannot be easily demagnetized by an external field. So for soft ferromagnetic materials such as iron, the hysteresis loop is narrow, as in this one here, which corresponds to a small remnant magnetization, and therefore soft ferromagnetic materials are easily magnetized and demagnetized, okay? And an ideal soft ferromagnetic material has no hysteresis and therefore would have no remnant magnetization. So to fully demagnetize a ferromagnetic material, it is taken through successive loops where the applied field is gradually decreased, as in this case, Also, another point is that the area enclosed by the magnetization curve represents the work required to take the material through the hysteresis cycle. So the energy that is acquired by the ferromagnetic substance in the magnetization process comes from the electromotive force in the circuit of the coil, which generate the current. Okay, so it comes from this electromotive force, um, and this produced the current, which produced the external field needed for the magnetization process. So when domains realign in the magnetization cycle, dissipative processes transform the magnetic energy into internal thermal energy, and this will raise the temperature of the sample. And this is why devices that use alternating fields, such as transformers, use cores made of soft ferromagnetic materials to minimize the energy loss per cycle. So we will now discuss paramagnetism. So the susceptibility of paramagnetic materials is positive and small. So chi is greater than 0 but much less than 1. And it is due to the presence of permanent magnetic dipole moments. So in the absence of an external field, the dipoles in a paramagnetic material are randomly oriented, and the interaction between them is weak. But if the substance is placed in an external magnetic field, the dipoles tend to align with the field, but thermal motion competes with this alignment process. Okay. Experiments found that for a wide range of conditions, the magnetization of a paramagnetic substance is proportional to the applied magnetic field B, and inversely proportional to the absolute temperature. So M is equal to CB over T. So this is known as Curie's law, and the constant C is known as Curie's constant. And so the magnetization increases with the applied field B and is inversely proportional to the temperature. So if B is equal to 0, then the magnetization is equal to 0, which means that the dipoles are randomly oriented. Also at high fields or very low temperatures, the magnetization approaches its maximum saturation value, which corresponds to complete alignment of the dipoles. Okay. So also going back to ferromagnets, if the temperature of a ferromagnet reaches or exceeds a certain critical temperature known as the Curie temperature, then the ferromagnet loses its spontaneous magnetization process, okay? And then it becomes a paramagnet, okay? So there is a transition from a ferromagnet to a paramagnet at the Curie temperature. For cobalt, this temperature is 1394 Kelvin, and for iron, it's 1043 Kelvin. So we will now discuss diamagnetism, and the diamagnetic substance is one whose atoms have no permanent magnetic dipole moment. So the atom in a diamagnetic substance has no permanent dipole moment, okay? But if an external magnetic field is applied to such substance, for example, like silver, then a weak magnetic dipole moment is induced in the material, okay? So, and this induced magnetic moment is in a direction opposite to the applied field. So also, although this effect of diamagnetism is present in all matter, it is weak compared to paramagnetism or ferromagnetism, okay? So to understand this, let's suppose we have two electrons in an atom orbiting the nucleus in opposite directions, but with the same speed. Because the magnetic moments of the two electrons are equal in magnitude and opposite in direction, they cancel each other out, okay? And the dipole moment of the atom is 0. But let's suppose an external magnetic field is applied, then the electrons will experience a magnetic force QV cross B in addition to the electrostatic centripetal force they are experiencing from the nucleus, right? And this magnetic force modifies the electrostatic centripetal force, resulting in increasing the orbital speed of the electron if its magnetic moment is antiparallel to the field, or decreasing its orbital speed if its magnetic moment is parallel to the field. And so the magnetic moments of the electrons no longer cancel, and the substance acquires a net dipole moment that opposes the applied field. Okay. So we will now discuss the Meissner effect, which is a property found in superconductors. So as we have seen in previous videos, superconductors are substances that have zero DC resistance below a critical temperature that is specific to the substance. Some superconductors also exhibit perfect diamagnetism, and this results in the applied field being expelled by the superconductor so that the field inside it is zero. And this phenomenon is known as the Meissner effect. So if a permanent magnet is brought near a superconductor, then the two substances will repel each other, as you can see here, and the permanent magnet will float above the superconductor. So thank you for watching, and please don't forget to like and subscribe. And I included some solved examples, and see you in the next video.